Hi everyone, welcome back to the ninth lecture of E635 Applied Linear Algebra. Um, this is module 2. In module 1, we started looking into this idea called inner products and uh, the associated idea of inner product spaces. Right? We have seen how inner product is an idea that is inspired by the dot product that we know in R3. Yeah, and we've seen how that rudimentary idea of a dot product can be abstractified with the axioms of the inner product, right? We have seen various inner products defined on various vector spaces defined over R or C, which are not just in tuples of numbers, but other exotic vector spaces. Okay, and then we ended the first module with mm, uh, with this idea that an inner product automatically defines the idea of length or norm for a vector which satisfies certain properties, yeah, which we are going to prove now. Okay, so let me share my screen. Right, so okay, so let us remind ourselves of the properties that we are here to prove now. um, V is an inner product space. Okay, and so from the inner product we define the norm like this, the length. Okay, and then the length must satisfy these properties. So there are names also for these properties. Let me just write these names uh, beside these properties. This is called homogeneity. This is called positive definiteness. Yeah, this is Cauchy-Schwarz inequality. This is triangle inequality. Okay, now on to the proof. Uh, this is obvious. Number two follows automatically from the definition of inner product because it's already embedded in the definition of inner product. So all we have to prove is number three and number four. Okay, so one and two are trivial. Let us prove number three and four. So for number three, we'll see two proofs. In fact, I will do one proof and the other proof I will ask for you. I'll give hints, but I will ask for you to complete the proof as a part of your homework. Okay, so let us see. So we have this thing. What does it say? I mean, intuitively, it's kind of obvious. Why? Because you see, uh, this inner product and its magnitude is in fact VW cosine of the angle between V and W. And because I'm looking at magnitude, I have to look at the cosine, magnitude of the cosine. But you see, magnitude of the cosine is between minus, so cosine is between -1 and +1. So magnitude is between 0 and 1, right? So therefore, obviously, this quantity out here is being multiplied by a number which is between 0 and 1. So the ratio of this to this is the cosine, which is a number between 0 and 1. So obviously this is going to be more than or equal to this number. Yeah, but this is intuitive and it works out only for R2 and R3. In general, for the inner product, why should it work out? Yeah. Mm. So we'll see that by just the very axioms of the inner product, this inequality, the Cauchy-Schwarz inequality, would be we'll be able to prove that Cauchy-Schwarz inequality is true. And because this is true, it would make sense to define the cosine of angle by taking the ratio of these two numbers. Yeah, it's not the other way around. For R2 and R3, it's the other way around. We use cosine to get the Cauchy-Schwarz inequality. However, now that we have extractified everything, we'll use so we'll prove Cauchy-Schwarz inequality independently from the axioms, and from there we'll define that this is the cosine. Okay. Now, so how do we do this? So suppose V and W are given to us. V and W are given arbitrary vectors in V. Okay, let us look at this particular vector, say V, and I look at VW, this inner product. I divide this by W's norm squared, and I multiply this by W. This quantity, in fact, will be very important for us later on. This is the so-called orthogonal projection of the vector V onto the vector W. Yeah, it's kind of, you can see that, this dot product, this is like, I'm just writing this here, although if you don't understand the meaning of this at this point, that is perfectly all right. Because this is, just compare this, with our natural understanding of the inner product. Yeah, so see, this is the unit vector along W, and this is the magnitude of the this is the magnitude of the the projection of V along the unit vector, on the unit vector along W. So this, in fact, is the difference between the projection of V on W and V. This will have a huge, profound meaning later on, but that's not important for us at this point to prove Cauchy-Schwarz inequality. What we'll do instead here is the following. We look at this vector and we notice the fact that now if I calculate the norm of this vector, this norm squared obviously is going to be greater than or equal to 0, right? Because this is by the very definition, not definition, yeah, in fact, definition of the inner product. Yeah, this is inner product of this with itself, and that is greater than or equal to 0 by definition of inner product. But then let us try and find out, expand this left hand side of this inequality. What is this? This is the big inner product between this and itself. So bear with me while I do this calculation. This must be greater than or equal to 0. Yeah. Now I'm going to use that sesquilinearity property. Yeah. So first I'll use linearity on the first variable. Linearity on the first variable would say that this is nothing but V inner product with V minus V W squared W, yeah, minus the scalar will come out V W divided by W squared and W inner product with V minus V W norm of W squared W. This must be greater than or equal to 0. I think I haven't made a mistake. Yeah. Okay, fine. Now I'm going to use linearity on the second variable. So that will give me V minus complex conjugate will come out because it's a scalar in the second variable. So VW complex conjugate W squared, this is a positive real number, so it remains the same, into VW, this, yeah, minus, this is going to be VW by norm W squared into WV, yeah, then minus minus plus. Once again, sesquilinearity property. So in the second variable, the complex conjugate will come out VW by W square is there, but VW complex conjugate will come out by W squared, and this is WW, right? I think it's all right. Yeah, this ought to be greater than or equal to 0. But now notice that this is nothing but complex conjugate, right? So this is the same as VW complex conjugate. And this is W norm squared. So they cancel out. And this guy out here is V norm squared. Yeah, is that all right? Now, this quantity, this quantity, and this quantity, they are all the same. Yeah, two with minus signs, one with plus sign, so one will cancel out. We can cancel this with this one. So what we are left with is, so ultimately this gives us V norm squared minus VW complex conjugate divided by W squared is bigger than or equal to 0, which is in fact the same as saying multiplying both sides with W squared and rearranging gives us magnitude of VW squared is less than or equal to V magnitude squared W magnitude squared, which is of course the same as saying VW less than or equal to V. That's Cauchy-Schwarz inequality, right? We are going to see a more intuitive proof of the same fact, but that the one that works only for R. So alternative proof for the case when V is a vector space over R. What is that alternative proof? Well, suppose say X is any arbitrary, say X is a placeholder, unknown variable. X is an unknown variable. Yeah, in R. Now define x v minus w and look at its norm squared. By definition, this must be greater than or equal to 0. But this is what? This is xv minus w, xv minus w. Once again, I'm going to do the same trick of expanding this out. This comes out to be x squared because it's not sesquilinear anymore over real number. This is just linear. It's just bilinear. So this is x v squared minus 2 times x v w plus w norm squared bigger than or equal to 0, right? Now compare this as a polynomial of the form ax squared plus bx plus c. And I'm saying that this is greater than or equal to 0 for all x in R. Yeah, which means what? What can we say in terms of the roots now for this? So what can be said about the roots of the polynomial x square v square minus 2x v w square. What can we say about the roots of this polynomial, given the fact that this quantity evaluates to a positive non-negative number for every real number x? What can we say about the roots? That is your question, which will be a homework. in continuation with that, you will also show that from the uh, inference about the roots, one can derive Cauchy-Schwarz inequality. This is your homework. Do this. Yeah. Okay. Now we come to this fourth one, the so-called triangle inequality. Once again, it's very simple. So we have V and W. So let us look at VW whole squared. Yeah. This is by definition V plus W, V plus W. If I expand this out, what do I get? I get V plus uh, VW plus WV plus WW. From the property of inner products, this is V squared plus 2 into real part of VW, because you see this is VW, the complex conjugate, because it's WV. WV is complex conjugate of VW, and so VW plus complex conjugate VW gives us two times the real part of VW. That's why, and this is W squared, right? Now notice that this is less than or equal to V squared plus 2 times positive the magnitude of real part of VW into W squared. This is further less than or equal to V squared plus 2 times the magnitude of this complex number. We were looking at only the real part of it. Now I'm looking at the magnitude of the original complex number. So that's why I have this inequality. And then I use Cauchy-Schwarz inequality to argue that this is nothing but 2 times VW, right? This is by Cauchy-Schwarz, But this is just the expression for V plus W, the whole square. Taking away the squares, this implies V plus W is less than or equal to V plus W. That's it. That's the end of the proof. Yeah. So this Cauchy-Schwarz inequality and the triangle inequality is, of course, one of the most important inequalities as when it comes to this idea of length of vectors. Cauchy-Schwarz inequality is perhaps the next most important inequality, if not more. Many different inferences one can draw by using Cauchy-Schwarz inequality. Some seemingly very difficult inferences one can draw. Like for example, using Cauchy-Schwarz inequality, you can prove in fact trace of A B, say A B. So let us consider A B to be real matrices. A B, say real n cross n matrices, and for all such n cross n matrices, trace of AB magnitude, yeah, is less than or equal to trace of A squared, trace of B squared. Yeah, if you feel uncomfortable, okay, let me make it easier. Then you can prove this one. Let me make it easier. AB transpose, AA transpose, BB transpose. Yeah. Looks not very easy, but you can prove this using triangle inequality. Also using triangle inequality, you can prove something like, say, x1 dot 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 xn and y1 dot 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 yn are, let's say, all real numbers. Then you can actually prove that summation xi yi, the magnitude of that, yeah, is less than or equal to summation xi squared product summation yi squared. Yeah. Or for that matter, you can also prove for two functions, minus infinity to infinity, f g dt magnitude is less than or equal to integration minus infinity to infinity f square. I forgot, so I can put a square here. Put a square here. Yeah. F square dt multiplied by g square dt. All of this will follow actually from Cauchy-Schwarz inequality. You know, without that without that Cauchy-Schwarz inequality defined for inner products, these proving these things independently may seem very difficult. But once you realize that this actually what is happening is the interrelation between an inner product and the norm, then using Cauchy-Schwarz inequality, you can actually prove this. So in fact, you see all this one, two, three, all these problems individually are three individual difficult problems. Seemingly there is no connection between them. But it turns out that all of them are actually the same thing. Yeah, all of them essentially are Cauchy-Schwarz inequalities for different notions of inner product. That is the strength, that is the beauty of abstractifying a concept. Okay, now, once again, as I said, so once you have proven all these things, now we can talk about this next part of our analysis, which says that once we have this Cauchy-Schwarz inequality, as I've said, one can define this notion of cosine of an angle between the two vectors. Yeah, right? Which would mean that one can also, in particular, define when the two vectors have 90-degree angle between them, or when the two are orthogonal. That would mean that the cosine of the angle is 0. Yeah, which would then necessitate that v dot product, v scalar product is equal to 0. So we'll not go into defining angles per se, but instead we'll use this property to define orthogonality of two vectors. So we'll say that VW two vectors in an inner product space V, then V is orthogonal to W if this happens. Obviously, by this is complex conjugate of WV, but that means if VW is 0, then WV is also 0. So that means V orthogonal W is the same as W orthogonal V. Right, so we say that V and W are orthogonal to each other, or V and W are orthogonal. Okay, this is the definition of orthogonality of two vectors. Yeah, simple, no? The moment we have the definition of orthogonality of two vectors, I can actually talk about orthogonality of a set. Okay, let S be a subset of an inner product space. Then S is said to be an orthogonal set, is said to be an orthogonal set if each pair of distinct vectors in S are orthogonal. That means Vi is orthogonal Vj for all Vi Vj in S I okay, Vi not equal to Vj. Vi not equal to Vj. Remember that this actually means that this is by definition Vi Vj. Yeah. Example of orthogonal sets. So in says Rn or Cn, Rn or Cn with the standard dot product, standard inner product. Yeah, with standard inner product. This collection E1, E2, dot, 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 up to En is an orthogonal set. In fact, this is also what is known as an orthonormal set because each vector has length 1 also. Not just that they are orthogonal to each other, they are length 1 also. This is true essentially because if you look at Ei, Ej, this is Ei transpose Ej, and that is the delta Ij function, which means it's 0 for all I not equal to j case. So it's an orthogonal set. So the idea of orthogonality is very simple. The dot product or the inner product must be 0 of two vectors. Yeah. So we are defining this orthogonality of two vectors only. Then we have a set which may contain various different vectors. We are saying that the set is called an orthogonal set if for every possible pairs, yeah, for every possible pairs, the pairs must be orthogonal to each other. Yeah, so it's a collection of, let's say, 10 vectors. Then I look at all possible 10 C2 combinations. Each of those combinations must be orthogonal to each other. That's the idea of orthogonality of a set. That's how we define an orthogonal set. Now, why go to such lengths as to define orthogonal sets? It turns out that orthogonal sets are immensely helpful. You just can't overstate their usefulness. So useful, so helpful they are. First thing that we notice is that an orthogonal set must necessarily be linearly independent. And the proof is absolutely simple. What am I saying is so let V be, and let me write it even more precisely. V together with this be an inner product space. Let S in V be an orthogonal set. Then S must be linearly independent. You remember the definition of linearly independent? It means you take any finite linear combination of distinct vectors in S. If it is 0, then all the coefficients must be 0. There is only the trivial linear combination of distinct vectors in S can take it to 0. Yeah. So for that, let okay, consider, suppose V1 dot 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 up to Vn in S are distinct, and alpha 1 V1 plus dot 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 up to alpha n Vn is equal to 0 for alpha I in the field. So linear combination is going to 0. I have to show that all these alpha i's are 0. Yeah, we have to show that alpha I is equal to 0. How do I do this? So consider alpha 1 v1 plus dot 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 up to alpha n vn dot product with or scalar product with vi. This is scalar product with 0, so that means that also is 0. Yeah, this 0 is a vector 0, this 0 is a scalar 0. But understandable. This by linearity in the first variable means this is alpha 1 v1 vi plus dot 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 alpha I vi vi plus dot 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 alpha n vn vi, that is equal to 0. But what we know about orthogonality, v1 vi must be 0 because it's an orthogonal set. Every pair is orthogonal to each other. All these entries are 0. This is also 0. Only we're left with vi, which is the same as alpha I vi norm squared. This is equal to 0. But this is a positive number, in fact, because vi is a non-zero vector. So it's a positive number. This implies alpha I must be equal to 0. And this is true for all I. Just take I to be equal to 1 to n. So alpha i's are 0. So the only linear combination that goes to 0 is 0. That's it. That's the trick. So it follows that the vectors are linearly independent. Okay. There is a great corollary to this result also. Not just that orthogonal set is linearly independent, but when we use that linearly independent set to express a vector, the expression itself has a very nice form. What do I mean by this? It's so important that it deserves to be called a different section. Representation of a vector in a representation of vector using an orthogonal set. Remember, orthogonal automatically means they're linearly independent, as we have just seen. So now, suppose, let S be, okay, let us consider this now. Let V1 dot 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 up to Vn be an orthogonal set. Consider a vector V to be equal to alpha 1 V1 plus alpha 2 V2 plus dot 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 alpha n Vn. Yeah. Okay, this is a unique linear combination because they are linearly independent, because V1 to Vn is linearly independent. Why linearly independent? Because they're orthogonal. Orthogonality implies linear independence. This unique linear combination, how do I get these alphas? We can get these alphas so easily because they're orthogonal, because V1 to Vn are orthogonal. Notice that if I look at Vi, this is going to be by linearity V1 Vi plus dot 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 alpha I Vi plus dot 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 alpha n Vn Vi. Just like before, each of these guys would go to 0 except for this one, except for the ith one. So this tells me alpha I Vi norm squared must be equal to Vi. So I get alpha I to be equal to Vi by Vi squared. This is true for all I, in fact, not any particular specific I. Yeah, combining, what does this mean? This means V then is nothing but, brace yourselves, huh? Here it comes. Summation I goes from 1 to n Vi. What are the coefficients? The inner product of V with Vi divided by norm of Vi squared. Yeah, is it all right? Each of these quantities are in fact called the projection of V along Vi. Indeed, once again, I've said this before. When we look at this Vi, this expression is this divided by, in fact, Vi into Vi divided by length of Vi. So this guy is the unit vector along Vi, and this is V cos theta. Yeah, indeed, because over R2, this is nothing but mod of Vi and cosine of theta divided by Vi. So this cancels out. So this is V cos theta. So this indeed is the magnitude of the projection of V on the unit vector along Vi. That's why this expression is the projection, orthogonal projection. So this is called the orthogonal projection of V along Vi, along the direction of Vi. Pictorially, it would mean, so suppose this is V1, sorry, this is V1, V2, V3, this is V, yeah. Look at this projection, look at this projection, and look at this projection. This quantity is, so this was V, this quantity is V1, V1 gives the length along the unit vector. This is this vector. This vector is V2, V2, V2 by V2. And of course, this vector is V3, V3. We write it the standard way. Okay, right. So this is how you express a vector in terms of as a linear combination of orthogonal vectors, right? So orthogonal vectors are so good. In fact, you can also notice that if instead I have V, so if we have Vi norm equal to 1, then the expression for V is in fact summation I going from 1 to n Vi into Vi. They are already unit vectors. So Vi square is just 1. So therefore it becomes like this. Let's just take the projection. That's it. Yeah. Remember that if the vectors are not orthogonal, then this is not going to work. This trick is not going to work. This is true only when this S, the set, using whose vectors I'm writing I'm expressing my vectors as linear combinations. This trick of just taking projection to get the coefficients will work only when the vectors are orthogonal. When they are orthonormal, then I don't even have to divide by the length. Yeah, just take the inner product and be done with it. This is called an orthonormal set. Yeah, so they're so powerful, so beautiful. So if you remember when we were, pre-MITSEM, when we were trying to find out, okay, somebody gives me basis vectors and asks me, okay, find out the representation of a given vector in terms of this basis. The question of the coordinate, right? So there, if you remember, it was a significant, but it was a significantly difficult problem. Yeah, the, somebody gives me vectors v1 up to vn and some another vector v and ask me to find out alpha 1 up to alpha n such that v is equal to alpha 1 v1 plus alpha 2 v2 and so on. And we have seen before that this, in order to do this, I actually need to set up this equation. So I write v1, v2, v3, vn. So I'm talking about n tuples. So v1 is an n tuple, v2 is an n tuple, and so on. So I stack them up one after the other, gives me a square matrix. Then that square matrix multiplying the vector alpha 1 up to alpha n must be equal to my given vector, given n tuple v. So I have to solve a linear system of equations to get this representation, right? But if v1 up to vn is an orthogonal set or an orthonormal set, then solving this linear, this linear equation is absolutely simple, because this alpha 1 is nothing but inner product of v with v1. Alpha 2 is inner product of v with v2. Alpha 3 is inner product of v with v3, and so on. Just take inner products and you're done. There is actually an analog of this situation with matrices. So when we have, suppose we are in Rn, and there we have an orthonormal set of vectors v1 up to vn. I write them up as columns of a matrix to form v1, v2, v3 side by side to get this n by n square matrix. Because the columns are orthonormal, this matrix is so-called orthogonal matrix. Call this matrix, say, U. Then it follows that U transpose U is identity. That is how one defines an orthogonal matrix. U transpose U equals identity. So in that case, if I want to solve U x equal to b, yeah, then I just have to multiply both sides by U transpose. So I have U transpose U x equals U transpose b. U transpose U is identity, so x is equal to U transpose b. That's it. That's the beauty of orthonormal vectors. But the important question now here is, okay, all good. If I have an orthonormal set or an orthogonal set, the expression becomes so simple. Solving linear equations also becomes very simple. But what is the guarantee that I will have such an orthonormal set in a given inner product space? We have seen that for a finite dimensional vector space, there will always be a basis, a finite basis. Yeah, that's just a basis, doesn't have to be an orthogonal basis, right? So if I have to use these great properties of an orthogonal set, an orthogonal basis, what is the guarantee that there will be an orthogonal basis? It turns out that there is a guarantee. There is this, amazing process which allows us to do the following. Somebody gives me a basis, not necessarily orthogonal, yeah, some arbitrary basis. From there, I can actually construct an orthogonal basis if my vector space is an inner product space. And that process is known as Gram-Schmidt orthogonalization. What is this process? It's stated in terms of a theorem. So let V be an inner product space, and V1 dot 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 Vn is a collection of linearly independent vectors. Is a linearly independent set. Then there exists W1 up to Wn, this set, which is an orthogonal set, such that for all m equal to 1, 2, 3, up to n, span of v1 up to vm is equal to span of w1 up to wm. So there exists an orthogonal set, first of all, and not just that, this orthogonal set is in fact a basis for this nested chain of subspaces obtained from V1 up to Vn. So let me explain this, what I mean by this. So I have V1 up to Vn vectors, linearly independent. So V1, span of V1 is a subspace, span of V1, V2 is a subspace that contains span of V1, span of V1, V2, V3 is another subspace that contains span of V1, V2, and so on, right? So V1, V1, V2, V1, V2, V3, and so on, okay? V1 up to Vn. These need not be orthogonal, but what we'll have is we'll have another set of another such nested chain. But the interesting thing is, first thing, they are orthogonal, so they are orthogonal basis. Not just that, they're orthogonal basis for the same subspaces. That means these two subspaces will be the same, these two subspaces will be the same, these two subspaces will be the same, and so on. So the same chain of nested chain of subspaces, but having an orthogonal basis now. Okay. Yeah. So how do we get this? The proof is by induction. Yeah. Proof by induction. Base step of this induction is just take W1 to be equal to V1. So this would imply W1 span is equal to V1 span. So first step is done. It's the induction on this number n. Now inductive step. So suppose the theorem is true for m, we have to show that this is true for m plus 1. Suppose suppose for m, that is m which is suppose for m satisfying 1, m strictly less than n, we have W1 up to Wm orthogonal set such that W1 Wk span is equal to V1 Vk span for all Km. So up to m, some number m which is strictly smaller than n, we have the theorem satisfied. Yeah. To show that there exists Wm plus 1 such that W1 span Wm plus 1 is equal to span V1 up to Vm plus 1, and W1 up to Wm plus 1 is orthogonal. That's it. If we do that, then we are done by induction. Yeah, you are understanding my point. I hope you do. Okay, so we have to find out this Wm plus 1 given this data. The beauty of Gram-Schmidt orthogonalization that it's constructive. It will tell you how to get this Wm plus 1 precisely. So this is the definition for Wm plus 1. So define Wm plus 1 as I have Vm plus 1 minus summation I going from 1 to m Vm plus 1 dot product with with Wi divided by Wi norm squared into Wi. Yeah, define Wm plus 1 like this. Claim is Wm plus 1 Wi ought to be 0 for all I going from 1 to m. Yeah. Now, why is that true? This is so. Yeah. So let us see why is this true. This is by linearity of the in the first variable. This is this minus summation I going from 1 to m Vm plus 1 Wi squared Wi. Oh, sorry, I have used both i's here. Yeah, have to be careful. J I is fine. Wj here like this here. So Wj I know are already orthogonal for all ij going from 1 to m. Yeah, so therefore this is 0 only for this one. So let me write this out and it should be clear to you. Wj will remain as it is, and among these terms here, all these terms here for all I going from 1 to m, only I equal to j will survive. So this will be Vm plus 1 Wj divided by Wj square. This is the same as this, so they will cancel out. And notice that this and this are the same. This is equal to 0, and this is true for all I. This is true for all j equals 1 to m. So what we have shown with this is that the way we have defined Wm plus 1, W1 dot 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 up to Wm and Wm plus 1, this is an orthogonal set now. This is an orthogonal set. Why is this an orthogonal set? I have to show every pair is orthogonal to each other. For all these vectors, I have already assumed by the inductive hypothesis that they are orthogonal to each other. So now this set will be orthogonal if the pairs where Wm plus 1 is there and anything from W1 to Wm, that must be orthogonal, that pair must be orthogonal to each other. And that is what we have shown here. Yeah, so there are how many equations actually? There are actually m equations involving j going from 1 to m. Then all of them are 0. So therefore, this is an orthogonal set. This part we are done. How to show that nested chain property? Well, the nested chain property already is true for all the way up to Wm. So all I have to show is that, so to show that span of V1 up to Vm is equal to span of W1, sorry, not Vm, Vm we have already shown. We have, not shown, we have already assumed 2 plus 1 is equal to W1 all the way up to Wm plus 1. Hmm. Now, why is this true? So first of all, notice the following. Notice that the way I've defined Wm plus 1, Wm plus 1 is in fact Wm plus 1 is a vector in the span of, let me write this out, then we'll verify. Wm and Vm plus 1. Why? Look at the expression for Wm. This is the expression for Wm. It's a linear combination of vectors W1 up to Wm and Vm plus 1. So I am not mistaken here. This is indeed true, right? So then this space, however, is the same as um, this is W1 up to Wm plus Vm plus 1. But what is this space? This space is the same as V1 up to Vm by inductive hypothesis plus Vm plus 1. These are linearly independent, so this is the same as V1 up to Vm plus 1, right? Which means my Wm plus 1, the new vector that I have created, that is a vector in the span of the given set of vectors V1 up to Vm plus 1, which then means that this span, no, W1 up to Wm plus 1, this is a subspace of V1 up to Vm plus 1, right? So this is a subspace. But now notice how many vectors do I have here? M plus 1, right? They are orthogonal. So this means there are M plus 1 linearly independent vectors. So the dimension of this is M plus 1. These are linearly independent, so this dimension is also M plus 1. So I have a subspace whose dimension is the same as the bigger space. So the two spaces must be equal. W1 to Wm plus 1 must be equal to V1 up to Vm plus 1. So we are done. This is the Gram-Schmidt orthogonalization process, which gives us, so given set of linearly independent vectors allows us to orthogonalize those vectors and get an orthogonal basis for the given set of linearly independent vectors. So pictorially, what is happening is something like this. See, we'll do it for first for 2 vectors, and then we'll see whether we can do it for 3 vectors. So suppose I have 2 vectors v1 and v2, right? What I want is, so this is a basis, no, they are linearly independent, so this is basis for R2. We want orthogonal basis for the same span of v1 and v2, but I want orthogonal. What I'm going to do is I'm going to define w1 exactly as v1, right? Now in order to get w2, what I'll do is I will project this vector v2 onto this w1, right? And what is that projection? That projection is this one. And then I will take the difference, and this I will call w2, and it will turn out to be orthogonal to w1. That's the beauty. So the difference between the original vector and its projection will always be orthogonal. That is what it tells us. You see the way I have defined here, w2 is v2 minus v2 projection w1 along w1. That is orthogonal. Yeah, so that's how I get w2. Now I have, so now the situation is, suppose I have 3 vectors. So for 3 vectors, suppose it's very difficult to draw 3 vectors. I don't know whether it will actually make sense or not. Suppose this is my given vector v. No, I have three vectors. No, it's going to be actually difficult. So um, we have to leave it to our imaginations. But this is, if you remember this one, then that's perfect. That is how Gram-Schmidt orthogonalization works. One can even modify the process a little bit and get an orthonormal basis instead of just an orthogonal basis. One can get orthonormal, that is Wi square is equal, Wi just, you don't need the square, Wi is equal to 1. That also can be done. All we have to do is that each time we define this new vector, we normalize it also. See, so like before Wm plus 1, yeah, I defined this as Vm plus 1 summation minus summation I going from 1 to m, Vm plus 1 Wi. They are unit vectors, so I don't have to do the division business. This is how I define Wm plus 1. W hat m plus 1 need not be unit length. Define Wm plus 1 as W hat m plus 1 divided by W hat m plus 1 norm. That's it. Then this will be an orthonormal set. That's Gram-Schmidt orthonormalization. To understand this Gram-Schmidt orthogonalization even better, what we can do is we can see how we are doing this for particular vectors. See, so suppose I take three vectors, example, v1, v2, v3. What I could not do for, with pictorially, let me show it to you algebraically. v1, v2, v3, linearly independent set. How do I proceed? I define w1 as v1, w2 as v2 minus v2 w1 squared, sorry, w1 squared w1. This is w2. w3 now will be v3 minus v3 w1 squared w1 minus v3 w2 squared w2. That's it. This plus this gives me the projection, because this projection along w1, this projection along w2, add them up, get the projection like before. Yeah, that is how we defined projection. Remember? Where was it? Here. Yes. See, this is how projection is defined. Okay. So the crux of the matter is that every finite dimensional vector space, which is an inner product space, allows an orthonormal basis. So this is the final corollary. Every finite dimensional inner product space admits an orthonormal basis. Okay, think about this, and when we meet for the third module, we'll see how this idea of an orthonormal basis allows us to get what is known as the best approximation. Okay, so till then,